Okay, first we want to show you this thing actually compiles. So here we go. And our screen capture thing is like a sliding program, so I hope it doesn't give you guys motion sickness. But so anyway, there you go. Successful compile.
So here we have the constants package, which has a number of values that we thought would be useful to various VHDL files. We'll start out by looking at the first two values. It's init PC0 and init PC1. Both are set to 0 off the bat. The reasons for this will be clear in a bit. Next we have the program counter increment, which is 4. So we increment 4 bytes every cycle for the program counter, and then we have the initial context, which is 0, just because that makes sense to computer scientists. We probably didn't need either of those, but just in case something happened, we have them. Next we have the register file size, which is 32. It's used in a couple of files, notably the reg file VHDL code, and it's also used in the dependency evaluator. So it can keep track of how many cycles until available there are for each of the registers. Next we have the two files used for the instruction caches. So right now we have sort.image, which is just the binary version of the sort code that we have, and stats.image, again, just the binary version of that. We also have some smaller test cases, which a few of which might be used in the course of this demo, and there's also an end.image, which just has one opcode, the end opcode, and when that runs, it kills that context right off the bat. Next up, we have the data memory, which right now is set to data2.image, which is just the numbers 0 through 31 and the first 32 words of the data memory, and then also in the second 32 words of data memory, they're randomized in there. So when we run sort and stats, they can use their own separate memory locations, and we can easily tell when the numbers are sorted because it's pretty easy to figure out the one comes after 2. It also gives predictable stats, which is nice. We also have a data.image, which has 32-bit, 32-bit integers that are random in there, which we'll probably see in a different demo later in this presentation. Next, we have some miss rates. The instruction miss rate is 0 because how often would an instruction actually miss when we can just use prefetching and the code flow is pretty clear. Then right now we have a data miss rate of 25%. During testing, we actually varied it from 0% to 100%, so all hits to all misses, just to make sure that the pipeline was working correctly. Then we have a 5-cycle delay. The memory module is actually clocked at twice the rate of the project clock, the big clock. So it's 5 times 2, just so it is actually 2 full cycles. We probably could have made this random whenever the miss occurs, but we chose not to. Then we have the cycle length, which is 20 nanoseconds, as said in the assignment. And then we have a few other variables that are less important, but are there just in case.
Okay, the first program that we're going to show is for context 0. It's a 4-line program. It adds R0 to R5 and stores that in R1. And here R0 always has the value 0, so this effectively just stores 5 in R1. And these are the hex codes for all of our operations. The second one just adds 6 and puts that in R3 or R2, and the third one just adds those two registers together and puts them in 3. So there's a data dependence here on the third line, and then it just ends. On context 1, we're going to be running a single line program that just says end. Okay, so if we pull up the waveforms, At the rise of the first clock cycle, we've got an NPC of 0, and that issues the instruction. All right. 420005, which is the first instruction, the first add. And that sets the cycles until available register to 4 for the first register, because it's got 4 cycles until it can be used. Then we flip the context, go to context 1, and that issues the instruction FC0000, which is just end. Then we flip back down to context 1, and we read the instruction on line 4, which is the this adding 6 to R2. And so that makes the cycles until available register for register 2 to be 4. And then it goes ahead and it reads what the next instruction would be, which is adding the 2 registers together. And it notices that that we have to wait for 4 cycles. So it has to stall for 4 cycles. Then we flip back up to context 1, which hasn't officially ended yet because the end hasn't gotten to the execute stage yet. But it does at right here. You can see the end flag for context 1 flipping up. So context 1 has ended, but context 0 is still stalling because of the data dependency. And then once the data dependency goes away, we flip back down to context 0. And at the rise of the next clock cycle, we issue this 406-11000, which is the adding. And then the program goes to completion right here. We can take a look at the reg file, and we can see that by the time that we're done, register 1 has value 5, register 2 has value 6, and register 3 has value 11, which is exactly what we want. Okay, so we've got a program that should demonstrate how we handle control hazards. It's a simple branch problem. We branch if R0 is equal to R0, which it is. Then we skip down and we just end the program. Otherwise, we add 12 to register R1. And we've got a branch delay slot in there as well. This is going to be run on context 0, while context 1 is going to be holding the single line end. So if we pull this up, so at the first clock, we are at the first instruction, and so it issues this C00008, which is this first branch instruction. It notices that it's a branch, and then it says that we need to stall for 2 cycles because we need to find out what the outcome of the branch is. So we flip up to context 1, and that issues its FC000, which is the end. Then at the rise of the next clock cycle, notice that the context hasn't changed because the first one is still stalling. We issue a no op because there's no other instructions for context 1. Then once the stall has gone away, we're now in the location 4, which is that branch delay slot right there. And at this point, you'll notice that the branch is changed so that instead of going to location 8, we go to location 12. And that says just to end, which is issued right there. And after a while, it does end. You'll notice that context 0 only ever issues this one branch right here and this end right here, which says that we actually did the branch successfully. And finally, if we look at the contents of our reg file, you notice that nothing has changed. They're all zeros.